Hey everyone, Max here. And so we're getting started with Chapter 18, and Chapter 18 is where we're introducing t-testing. And so just as a brief recap, what we did last lecture session was we essentially learned how to hypothesis test for the mean, okay? That is, we've been dealing with random variables distributed as n, mu comma sigma, and mu sigma completely determined our distribution. Our distribution. And what we're working with now is we're going to be working with, let me add the little inflection points. The inflection points being where this nice frowny face, the hump, turns into the smiley face, right? And those are at mu minus sigma, mu plus sigma. And we know that to test for an unknown mu, right? We want to estimate the mu for some population. To test for this thing, we use a z-test, as we've called it. And if you recall, this z-test has the z-test statistic of x bar minus mu naught over sigma over root n. And this mu naught, again, was our null hypothesis. And this x bar was our estimate, right? Because the sample mean estimates the mean. So this is, of course, our estimator. And we had our theoretical values. So we had a theoretical sigma and a sample size. N. And the key note here was that we had the sigma sample size, the sigma standard deviation. And so what we're going to start talking about now is we're going to start talking about, in contrast, we're going to start talking about the t-distribution. We're still going to be testing for the population mean. So we're still testing for population mean. We're still testing for population mean. Then we obviously, or maybe not obviously, but we need different tools. Okay? The tool, that's toll, sorry. The tool is the t-distribution. Okay? And this t-distribution specifically is going to look a lot like the normal distribution. Okay? It actually looks so much like the normal distribution. But we're able to, instead of it being centered at mu, so this is normal is centered at mu, which is why means are so important, because the normal distribution is determined by the mean and the standard deviation. The t-distribution of nu, or TDF, we'll talk about what these mean, okay, is how a random variable, we'll call this one y, can be distributed. They can be denoted with a T new, it looks like a fancy V, or a T sub df, and we'll talk a little bit about what those things are. Again, that's a y and then a tilde T, and you either have a new or a sub df, and we'll talk a little bit about what those are. But this, we get to assume without loss of generality that it's centered at 0, and if you look at your table in your textbook, at table C in the appendix, you see that it has a T star, a negative T star, and it says that this is at 1 minus C over 2. And what it means is that this shaded area right here, if we think about it in terms of that kind of mysterious alpha we've been talking about, that is our significance level, the area is actually equivalent to alpha over 2. So alpha is equal to, say, you can think about it as being like this. So if we were thinking in terms of, say, 95, alpha is 0.05. This is just going to be, which implies a 5%. This implies that this is about 2.5%. Okay. And what this is going to do for us is we don't have to know a standard deviation like we did with the normal distribution, and we won't have to know a mean. What it's going to help us do is, with some more relaxed assumptions, actually determine what a population mean is going to be, okay? So, when we're thinking about how we're actually going to use the t-distribution in a t-test for hypothesis testing, we need to think about the assumptions that we really emphasized beforehand, okay? So let's think just a little bit about these assumptions, and I'll talk more about this new in the DF, okay? But first, I want you to be aware of the assumptions for which we're going to use this test, okay? So the assumptions, which are given in the notes, here I'll give you a quick look. If we look right here, I'll just underline them real quick. These are the assumptions, okay? And they're very important, and we'll talk about them right now. Okay, so this is one that is going to stick with us throughout the rest of our courses. We have an SRS, or we may not necessarily always have a perfect SRS, but we will have something we can consider an SRS. We then have our data normally distributed so we take a sample. So if we're thinking about all the students in our class and their heights, we take a sample, and then we have data, and it looks like this. So data looks like, okay. And so but this we may also not always know. In practice, we'll settle for single peaked and symmetric. Okay. And then the last assumption. The last assumption is going to be that the population is much larger than our sample. As a heuristic, we say it's about 20 times larger. So that is, you don't want to use this testing, you don't want to use this method of testing the t-test on, say, like a group of people that's only 50 people and you only sampled 10. So you don't want to use a t-test then. You want to make sure that you're taking a sample from a very, very, very large population. So if I took a sample of, say, 50 people out of the entire student body at the University of Utah, which is about, I think, 30,000 or maybe a little more, okay? Or closer to 40,000. That is definitely more than 20 times 50 people. So that would be appropriate. And this last part, it's not an explicitly stated assumption. It's what I want to draw attention to of a lot of students, and everyone is going to ask, other than the assumptions, so I'm going to write common question. Other than the assumptions, how do we know to use a z-test or a t-test? And this comes down to something pretty straightforward. If you look at the two formulae, so we have, and for the z statistic, x bar minus mu naught over sigma divided by square root of n. For t, we have that x bar minus mu naught over s over square root of n. And if you look, this is the same, this is the same, this is the same. Of course, the statistic names are different, but you have that sigma and s are different. And just as a quick reminder, sigma is the theoretical standard deviation. Now this is a theoretical value. You will almost never, if ever, have a theoretical standard deviation value. The only instance in which you would maybe have it is if everyone decides that says, okay, our theoretical standard deviation value, we're all going to pretend is this value. That is maybe the only instance, and you'll most likely never see that. But something that you've done yourself, and you will most likely almost always have, is S, which is the sample standard deviation. So when we're thinking about the problems in which you're going to have to determine, do we use a z-test or a t-test, you're going to look at the two formulae, and if you just look at it like a work of art, you look at it just visually, you'll see the only difference is this sigma and this s. And so you have to ask yourself, do I have a sample or theoretical standard deviation? And I'm just going to abbreviate standard deviation as SD, okay? And if we have a theoretical, we're going to use the Z, okay? So theoretical. And again, if we have a sample, we're going to use the T, okay? Now, you might say, well, how am I going to know if there's a theoretical or a sample? And I'll give you just a few examples. For a sample, it'll say S is equal to some number. It'll say was computed, because you compute the sample standard deviation, or it'll say something like the sample, and then it'll say standard deviation, again abbreviated as SD, and it'll trail off. For a theoretical, it'll say sigma is equal to say x dot x, or the theoretical dot dot dot, or it'll say the standard deviation is dot 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 dot. You have to have some indication somewhere in whatever context you're working with that you either have a sample or an accepted theoretical, and that's how you'll tell the difference, okay? And the reason that this is so helpful specifically is that, as I said before, let's do some erasing real quick. As I said before, let's erase these assumptions right here. As I said before, oh shoot, I can't remember what I was about to say. This is bad. As I said before, we're talking about the assumptions. How do we know to test for z-test? Sample was computed. As I said before, the reason this is so useful, as I said before, is because for a normal mu sigma, you need to know this, which is why when you do a z-test and we're assuming normality, we need to know this theoretical value, right? Because this is mu minus sigma, mu plus sigma, okay? However, for a t, as I said before and mentioned very, very briefly, we could assume this is at 0. We can say t star. We can say this is negative t star. Do some shading. T of nu, okay, it's a fancy v, or t of the degrees of freedom is completely determined by its degrees of freedom. Okay. And because it's completely determined by its degrees of freedom, we need to know how to find this. So we'd say, how do we find nu? Or as is denoted by df. Either is acceptable, okay? df, of course, meaning degrees of freedom. And this is actually quite simple. It's sample size minus 1. So nu is equal to n minus 1. That is, more precisely, the entire t distribution is determined by its degrees of freedom. That is, we know every single thing we need to know about the t distribution so long as we know the sample size. So, which is n minus 1, where n is the sample size. Okay. So let's go and just keep going a little more with the notes. We talked about these assumptions, we talked about this, we talked about the different forms, And just as a nice quick little note that I'll make for those of you who are interested, the reason these degrees of freedom are popping up randomly in the T is that a T distribution of, say, new degrees of freedom is actually distributed as taking a standard normal distribution, so right, where this is n, 0, 1, and dividing it by the square root of another distribution we'll talk about later in class, which is the chi-squared of new degrees of freedom divided by new. Okay, and that's just something that you can look up if you'd like to, but this is just where that degrees of freedom is actually coming in. It's coming in from this chi-squared. And the chi-squared part, just as another quick mention, the chi-squared of new degrees of freedom is actually just the summation of normal 0, 1 squared. I is equal to n to, say, to new times. Okay, so it's just a summation of standard normal random variables squared. And again, that's just for those of you who are curious and want to look something up. That's not something you need to focus or worry about. Okay, so that's just all this first page of notes is really talking about. Okay, and this is the last thing I'd like to call attention to, and I'll underline it right here. S over square root of n has a special name, and it's called the standard error of the sample mean. Okay, so if we ever mention the standard error, then, that is, if we ever talk about the standard error, we're talking about this right here, S divided by the square root of n. Okay, and that's all you really need to know about as an introduction to this. Okay. So moving forward, we'll start getting into how to actually use a t-table and the